So this is actually work of a master student that I supervised. His name is Ken Voskuil, with a famous "uin" sound. And yeah, so he couldn't be here today. He is currently working on his master thesis on a completely different topic. So he preferred me to give the presentation, but everything of the results and experiments is actually his work. And it's one of those, we say, engineering type projects where we have a problem and we need NLP to solve it. And we did it before with the by then state of the art, and now there is a better state of the art and we see if we can improve it. So in that sense, experimentally speaking, it's maybe not that exciting. It's just applying models to a new problem. But I think the problem in itself is very interesting, and yeah, we can get some interesting insights about patterns. So let me introduce this problem. There is a field of study related to the relation between science and inventions, science and innovation. And an important question that comes up in research policy, for example, is what kind of science leads to new inventions? And to study those questions, people analyze the citation relations between patents and science. But typically, in previous studies, only the front page references are used for this. This is the metadata that comes with the patent. On the first page is a list of references. And it has been shown actually that front page references and in-text references, so that is like how in academic papers we refer to other papers, so also patents do that. You refer in the text itself to previous work. And it has been found that these in-text references actually serve a different purpose than the front page references, where the front page references are mainly meant to argue for the patentability of the invention, to show that it is really new. Are the in-text references more related to the underlying science, so to motivate the methodology? A bit related to how it is done in academic papers. And therefore it has been argued that actually if you want to study the relation between science and innovation and which science ends up in patents, it's actually more relevant to study the in-text references. But they are sometimes and often more difficult to extract than the front page references. So here's an example. This is a front page of a patent. And this is where these are the front page references. And if you, for example, go to Google Patents, they are actually listed in the metadata part of the HTML, of the XML. So when you download a patent in XML form, you get this as a more or less structured list. And there's lots of information there in the complete titles, for example. On the other hand, if you look at in-text references, they are much shorter. Many of these, as opposed to scientific papers, don't have a full reference list at the end. Some do have, but not all of them. And you only have the information that is listed here, which is author's year, and then the specifics of the journal and issue and page numbers. But it is, as you can see, it is rather specific. But so far, before we started this, which is over 2 years ago, actually working on this topic, so before this particular student worked on it, only rule-based methods has been tried with the idea that it's so structured, we must be able to do this with patterns. But that appeared to be way more difficult than they thought at first. So what we decided to do, so my background is in NLP, and I do a lot of text mining. So my idea was, okay, but this is similar to named entity recognition, right? It's a sequence labeling problem. So let's address the task like that. Can we extract these sequences? And then once we have extracted references, let's match them to a publication database to actually identify which papers they refer to. This is the data that we have. We have training data, that is data that we labeled manually. And we have a full domain collection. So we took one ICPC code, so that's one domain in the patent collection of Google Patents. And there were 33,000 patents. It's all biotechnology, published between 2006 and 2010. So yeah, this is quite a similar sample, and that's the topic and the period. As collection or as database where we match the references to, we use the Web of Science, which has metadata for a lot of published journal articles, and also a table with the journal titles, full titles and abbreviated titles, which we need because, as you can see, these were all abbreviated in the text with some standardization, not always, but some, there is some, like J means journal, M means American, etc. Okay. So the steps of the total process actually is, of course, first we need to pre-process and annotate the data, then we train the sequence labeling methods and we evaluate them for the extraction. After we have extracted references, we do the matching against the Web of Science, and then the fourth step is filtering them to filter out the front page references, because those are duplicates and we are interested in the references that are only mentioned in text. The focus now is on the first two steps, but I will show the results for the full collection after matching and filtering. But that's not what the student did, and that's not what I'm presenting here. So in case you think, I have the feeling I heard this story before. Yes, that is true. If you were there in 2019 at Berndel, so that is beer, but then a bit broader and co-located with Ségayar. That day it was 40 degrees Celsius in Paris, but we were there in a dark and cool basement in the conference center, and I presented this paper. Then with another master's student, Johannes. And what we did then, we did the sequence labeling with conditional random fields. We still use that a lot. It's a feature-based sequence labeling method, and it's really effective still for many named entity recognition problems. And I still teach my students also to use conditional random fields and how to do that, not always directly move to the transformer-based models. But Johannes also experimented with a by then state-of-the-art transfer learning approach using the FLAIR framework with embeddings. You can read it in that previous paper. So what it can do, the master student of this time, he first improved the data quality because he discovered quite some inconsistencies there and tokenization errors and things like that. So a very practical task that you probably recognize that it is often needed, improve the data. And then he trained and evaluated BERT models to the task. So very briefly about this data quality, it's relevant to mention here that we use IOB labeling. If you have some familiarity with named entity recognition or NLP in general, you probably recognize that. It's a way where we label the words token by token, saying that or indicating that tokens that do not belong to a reference in this case are labeled O for outside, tokens that are the beginning of a reference are labeled B, and tokens that are inside a reference are labeled I. So it's a token level, and then the sequence labeling model learns the order of the B, I, and O's. So there was lots of problems here with tokenization related to the punctuation, where we first had a tokenizer that didn't do that very well, and this was improved. Also, there were quite some like sequences of multiple references, and Ken discovered there were some errors made there, and some of the references in the text were not correctly labeled. So he sort of relabeled the whole corpus. And then we had the training set contained 2,318 in-text references, so in 22 patents. So that's, I mean, 22 is really small, but in terms of number of training items, that's okay. Then in the pre-processing, well, long story short, we split the documents in sequences of 64 tokens. We looked into sentence splitting, but that was not relevant at all since patent texts have incredibly long sentences. So in the end, Ken decided that it's the most robust to just go for the 64 tokens. The only requirement was that subword tokens that the BERT uses are kept together for one word. Right, so there is a small risk that references are split up. And of course, we can, in the training data, we know the labels. We can say, okay, don't make a sequence split between a B and an I or between two I's. But in the test data, of course, we don't know that. So yeah, we take the risk, we just split it in 64 tokens. Or maybe I didn't mention it, but this is one of the limitations of the BERT type models, the transformer models, is because of the heavy processing of the self-attention model, they need a shorter input length. You cannot just give a whole document at once, or in the case of patent documents, even a whole sentence. So you need shorter input sequences. Okay. Then the BERT models that we trained, or that Ken trained, maybe as you expect, we have BERT with BioBERT, with SciBERT. Actually, there was a very interesting presentation yesterday. I tweeted it also, where in the main conference yesterday, where these three were also compared, and that's often the case in these kind of domains. So maybe for completeness, BioBERT is a further training of the regular BERT, not with a new vocabulary, but just adding biomedical articles to the original BERT model. And SciBERT actually is a pre-trained from scratch on scientific literature. Okay, so if you want all the specifications, you can go to GitHub. So here are the results for the extraction. We did it with a leave one patent out validation. So 21 patents to train on, one to evaluate on, and then we could cover all. So first I show the effect of improving the data quality, and well, this is strong, really. So there's a 5% point increase. I marked this in blue because this is what belongs together. So this is the improvement for the B labels, and this is the improvement for the I labels, and you see both of them get a 5% point improvement almost. Here it's a bit lower. So yeah, that's substantial. I also show here, but that actually comes from the previous work, we did not rerun FLAIR. It actually had a lower precision and recall than CRF, but in the end it retrieved more references from the large collection. The discussion of that is in the other paper, but I want to show it for completeness. Now, the results for the BERT models, they are higher than conditional modeling fields. We also have the results on the original data, and that shows the same difference. But as you can see, I underlined the best results here. We get very high F scores here to 98% performance and recall, which is the most important metric here. More than 97% for the I labels and 95% for the B labels. And that is extremely high. So normally I tell my students, whenever you train a model, you get 95% F1, be suspicious. But in this case, this is actually the case. So the structure of these citations is so clear, apparently, that the models can learn this. Yeah, this was an error analysis. Let me go to the next step because I'm a bit limited in time. But I wanted to show you that Ken did a little bit more on analyzing the differences between the BERT models and the CRF models, showing that CRF is really suffering from the long sequences. So we get this kind of strings out, and they're not always fully correct, but still, if we have sufficient information, we can match them to the publication database. So how do we do that? We analyze and parse them, match the fields to the database, and we count the number of matching fields to determine the strength of the match. And this is then what we see on the large collection. So this was a very good remark of one of the critical peer reviewers. That was very just to say, this is the results from the previous papers on the old data, right? So it's not a direct comparison, but it's just to show that we extract an enormous amount of citations here. And what this is, so this is the total amount in the years that we are after. So we have a range 1980 to 2010, I believe. So this 1.8 million, this amount could be parsed by our rule-based parser. The gray is the ones that have a definite match to the Web of Science, and yellow is the ones that are not on the front page. So in conclusion, we found, first of all, that improving the data quality had a large effect on the extraction quality. And second, we get a really good result from the BERT models with up to 97% recall for the BNI labels. And in total, in our collection of 33,000 patents, we find 736,000 citations that are not listed on the front page. So we get a substantial amount of additional links. This is for future work, but I will round off here. We got a project funded by the European Patent Office to further improve this. The extraction is okay now, but there is much more that we can do still. And one of the things is improve the matching process, because in this 700,000 references are definitely around 10% or so false positives. So we are still improving that. And in the meantime, my colleague Jian Wang, who came up with this whole problem, he's the problem owner here, we wrote a paper on the relations between what we can learn from the in-text references. It has been submitted to research policy. So sorry to go over time, but if you have any questions, please go ahead. This is the website of my research group, and you can also follow me on Twitter. Thank you.